Okay, this is part 2 of the video about pitfalls in understanding the probability distributions. We in the first part we covered the probability. PDF is not a probability subject, right? We said PDF is not a probability. We said PDF is the density, and then we finished that video with saying the following. Um, we said in order to get to a probability from a density, we always need an interval. So we take this density and then multiply by the interval on your variable axis. And if it's a wide interval, obviously your probability is going to be bigger, right? It's more likely the variable will fall into that interval. If it's a narrower interval, then probability will be smaller. Right? So you take the density can be high or can be low, and your interval can be wide or can be narrow. So these are different things, density and the interval, right? You need an interval to get to the probability of being in that interval. You need density and an interval width. Now, that brings us to the next interesting subject. It's the difference between countable and finite. So if you go to that bionic turtle video, which I referred you to, and that is in, let's see, that's going to be around 6-minute mark, I think. You are going to see that in that video the instructor talks about discrete random number variables as counted and finite. So it's in this video it gives you an impression, basically implies that countable and finite are probably the same. So when they talk about discrete, they always talk about countable and finite. Right? So I'm going to say, I'm going to say it's not true, right? Discrete distribution can be infinite, like Poisson distribution, right? But before we go there, let's look at even more interesting and subtle problem. And the problem goes like this. I'm going to ask you this question. What is the probability of observing a value 0 of a Gaussian random variable, but not just Gaussian, also a standard normal? Standard normal variable, it has a mean at 0, right? Standard deviation of 1. We know the density, well, we can calculate. So we can calculate the probability, right? I said exactly 0. What does it mean? Well, it means the following, right? How do we calculate it? We get the density multiplied by the width of an interval, and I said it's exactly 0, which means the width is exactly 0, right? It could be a little confusing, but I'm saying it's not an interval, it's just a point, 1.0. So we take the density and multiply by what? By 0, because our interval width is 0. We are interested in a point, probability of a point. So probability of a point is 0, and you could see, although the density is not 0, the probability of any given point, like in this case I picked 0 with the highest density, yet the probability that a Gaussian number will be exactly 0 is 0. Any number you take on a point, -2, -1, whatever, the probability of encountering that precise number point will be 0. Probability of a point is 0. But how then, if we add up all the probabilities of each point on a line, and each probability is 0, how do we get the total to 1? If we add up all the zeros, how do we get 1 in the end, right? Is it possible? So the answer is somewhat complicated. It goes into real analysis, measures, sets, and things like that. And I'm not going to do it here, but I will refer you to real analysis and sets and such. But I'll say here the following. So if you have a countable set, an example of a countable set would be 1, 2, 3. That's countable set. 1, 2, 3, 4, 5, 6. That's countable too. But also, if you take all the, let's say, non-negative integer numbers, whole numbers, 0, 1, 2, 3, 4, 5, and so on to infinity. That is also countable. By definition, what's countable? Countable is a set which you can number, 0, 1, 2, 3, with integer numbers, right? That's a countable set. And so if you have a countable set and probability of each point in this set is 0, and then you add up all the probabilities, you're still going to get 0. Countable set, natural numbers, and so on. However, there are sets which are not countable, real numbers. So let's say real numbers from 0 to infinity, or real numbers on 0 to 1 interval. It's rational numbers, irrational numbers, whole numbers, everything. That's real numbers, right? So the real numbers are not a countable set, which means that for real numbers, if you add up all the zeros, probability of 0 of each real number, but you add them up, you may get something greater than 0. You may get something greater than 0. So let's just state a couple of things without going into theory, right? Countable can be infinite, like I said. Let's say natural numbers, 0, 1, 2, 3, and to infinity. That's a countable set because you can count it, 1, 2, 3, 4, but it's infinite. It doesn't have bounds, right? So negative, non-negative whole numbers. However, infinite set can be not countable. Uncountable, I said, not countable, right? So countable can be infinite, but infinite can be not countable, right? So for instance, I gave you already the example of real numbers. I said all the real greater than 0 or 0 and greater, but even not that. It's even if you get a bounded interval 0 to 1, the real numbers on that interval are also not countable. So coming back to this confusion in the video, right? When they said, well, discrete numbers, they are counted and finite. Well, Poisson distribution, right? It's a discrete distribution, but a set of its outcomes is infinite. It's from 0 to positive infinity. It's infinite, but it's countable, right? Because you can map every outcome to an integer number. And in this case, they are integer, non-negative integer numbers. An example of a continuous distribution is beta distribution, right? So think of the beta distribution, right? It has finite bounds. So beta distribution is defined on the segment, line segment 0 to 1. So it's bounded from 0 and 1. So the values of beta distributed numbers cannot be infinite. They're always between 0 and 1. But the number of outcomes in beta distribution is not only infinite, it's all the real numbers from 0 to 1, but it also is not countable. You cannot count them using integer numbers, the outcomes of beta distribution, right? So discrete distribution can be infinite, but they're always countable. Discrete distribution can be finite, such as Bernoulli, only 2 outcomes. Now, the continuous distributions are, their outcome set, I would say, is usually not countable, right? It's not countable, but the continuous distribution can be bounded. Let's say 0 to 1. They don't necessarily have to produce infinite numbers, right? So this subject is, I would say, is not the central subject in what we study, but it's an important one, right? So it's related to measure theoretic foundations of probability theory, and PDF is closely related to a notion of a probability measure. And probability measure, for instance, is an important concept in any kind of options pricing theory, asset pricing, interest rate options, and so on. they operate in those fields, the scientists and quants, they operate with PDF-like things, the measures, probability measures all the time. They take measures and convert them from real world to risk neutral and so on. So they operate in these very esoteric spaces and concepts. So on that I'm going to finish this discussion, and again we covered these two, I would say, quite common pitfalls of understanding the probability distribution. That I'm going to say PDF is not a probability, and the often encountered confusion between countable and finite.